Question 13 from section 1 of the 2019 National 5 Physics Examination. A solid substance is placed in an insulated container and heated. The graph shows how the temperature at capital T of the substance varies with time small t. To calculate the specific latent heat of fusion of the substance, a student would use the time from section and you're asked to give the correct section of time. Now we know that the equation is E equals mLF, where m is the mass of the substance which has been heated, LF is the specific latent heat of fusion. So to work out the specific latent heat of fusion, we'd have to find the energy and divide it by the mass. So that's our key equation there. How do we find the energy? Well, we know that the energy is equal to the power times the time. So we know the power of the heater and we know how long it's in operation for. We can work out the energy supplied. Now the clue for this graph is the following. During a change of state, the substance temperature remains constant. There's no increase in temperature. Now, if we look very close, we know that the substance started off as a solid. So the first flat part of the graph indicates a time where the substance temperature is not increasing. In fact, that's where it's changing state. So we have here along the first flat part the changing of state from solid to liquid, melting or fusion as they call it. And the top flat part is really the changing of the substance from liquid to gas, which is called evaporation. Now we're after the specific latent heat of fusion of the substance, so what we'd be wanting to find out is the time along this section here, QR. If we can find that time, we could plug it into E equals PT and then put it into the top equation and find the specific latent heat of fusion. So answer to 13 is QR, which is answer B. Question 14 from section 1 of the 2019 National 5 Physics Examination. The pressure P due to a liquid at a depth h is given by the relationship P equals rho GH, where rho is the density of the liquid and G is the gravitational field strength. A liquid has a density of 990 kilograms per cubic metre. When the pressure due to a liquid is 1470 pascals, the depth of the liquid is, and you're given your 5 choices. This is just a case of rearranging the equation P, pressure equals rho, the density, times the gravitational field strength, times the depth h. So we're rearranging that equation, so we'll have h on its own. So to find h on its own, all we have to do is divide everything by all the quantities except h. So we have pressure P divided by rho times G, and that should give us a value for h. So therefore h, if we plug in the numbers, is going to be the pressure P, which is 1470 pascals, divided by, and we'll put a bracket around this, the density, which is 990 kilograms per metre cubed, and times the gravitational field strength, which is 9.8. So a calculation, we take our time and do that on our calculator, we get an answer of 0.151515, which will cut down to 0.15 of a metre. So question 14 will be answer B. Question 15 from section 1 of the 2019 National 5 Physics Examination. A car is parked in the sun for some time, and during this time the air pressure inside the tyres increases. The reason for this increase in pressure is, and we're given 5 statements. Now to help us answer this question, I'm going to do a little bit of revision and head over to that PHET site again for some simulation with pressure and with temperature. Okay, welcome back to the PHET simulation site where we have a container filled with a gas. You can see the particles of the gas moving about, colliding with the walls of the container. And imagine that container is just like the tyre in the hot summer's day. You can see we have a pressure gauge. There's also a thermometer at the top. And if you look at the far right hand corner, you can see that we're measuring also the average speed of the particles, which gives you an indication of the average kinetic energy of the particles. Now, let's go through each of the phrases or the sentences in turn about this gas. And let's first of all look at what's happening when we increase the heat into the system. So imagine the heat is increased into the system. You can see that the temperature is rising, the average speed is rising, and the pressure has risen. So let's go through each of the statements in turn and see if we can find out which is the correct statement. Statement A is the volume occupied by the air particles in the tyres has increased. Well, the volume occupied by air particles has not increased. As you can see, the volume of the container has stayed the same. So statement A is incorrect. Statement B, the force produced by the gas particles, the air particles in the tyres, acts over a smaller area. Well, the area hasn't changed, it's not got bigger or smaller, so therefore that statement is incorrect as well to explain the increase in pressure. Statement C, the average spacing between the air particles has increased. Well, no, the average spacing has remained roughly the same. So that statement is incorrect. Statement D, increasing the temperature has made the air particles expand. Well, that's not the case either, because the small spheres representing the molecules hasn't expanded. They haven't expanded, so therefore statement D is incorrect. It's the final statement, statement E, which is correct. The increase in pressure on the tyre is due to the air particles moving faster. I've got a bigger average speed, therefore they'll have a bigger average kinetic energy. So it's a greater kinetic energy, and therefore that means more collisions per second with the walls of the tyre or the walls of the container, which means the pressure will increase. So the answer for this question is statement E.